Hello my friends, today we are going to learn how to scale based on the number of messages in an SQS queue. SQS queues can be used to determine the load on an application, and combined with auto-scaling, the instances can be scaled in or out depending on the volume of traffic. We are going to understand how the solution works by writing an application that emits custom metrics to CloudWatch and by using a target tracking scaling policy. We will be using Terraform and the serverless framework technologies. All the code will be available on my GitHub. Link is on video description. Let's now discuss the solution. The solution is to use a backlog per instance metric, with the target value being the acceptable backlog per instance to maintain. I'll explain. Backlog per instance equals to SQS approximate number of messages divided by the number of running instances. Approximate number of messages is the available messages for retrieval from the queue. Running instances is the number of instances in the in-service state in an auto-scaling group. Acceptable backlog per instance equals to the accepted latency divided by the average message processing time. Accepted latency is what your application can accept in terms of latency. Average message processing time is the average time it takes an SQS worker to process a message. To illustrate with an example, let's say that the current approximate number of messages is 8 and the running instances is 2. If the average processing time is 0.5 seconds and the longest acceptable latency is 1 second, then the acceptable backlog per instance equals to 2. This means the 2 is the target value for your target tracking scaling policy. If the backlog per instance is currently at 4, then your auto-scaling group scales out, and it scales out by 2 instances to maintain that proportion to the target value. As we saw in the example, the module responsible for the scaling activities is the target tracking scaling policy. This policy is a dynamic scaling policy that increases or decreases the current capacity based on the target value. In our example, the target is the acceptable backlog per instance. This policy is very similar to the way your thermostat maintains the temperature of your home. Down below, you can see a screenshot of 2 CloudWatch alarms. The first, a scale-in alarm, scale based on 15 data points. The second, scale-out alarm, scale based on 3 data points. We can clearly see that scale-out is much faster than scale-in. So basically, once defined, target tracking scaling policy does the work for you. The following diagram illustrates the architecture of this configuration. There are 4 main parts to this configuration. The first one is an auto-scaling group which manages EC2 instances for the purpose of processing messages from an SQS queue. The second is the calculate backlog per instance lambda function that runs every minute. This function calculates the current backlog per instance by measuring the number of messages in the queue per EC2 instance in the auto-scaling group. The third is a target tracking scaling policy that configures your auto-scaling group to scale based on the custom metric. CloudWatch alarm will invoke the scaling policy. The fourth is the log auto-scaling event lambda function. This function logs auto-scaling events to CloudWatch log. This function is only for debugging purposes. Okay, now that we understand the architecture, let's dive into the code and view the demo. Let's review the code for this project. I'll give a high-level overview of the project and show the important pieces related to the scaling based on AWS SQS. The project contains 3 sub-projects. The first one is the backlog per instance calculator. It is a serverless framework project responsible for building and deploying 2 lambda functions. Each serverless framework project contains a serverless YAML file. This file is the main configuration file, and its responsibility is to define the different serverless components and the relation between them. This video is not about this framework, so I encourage you to check it out. The first Lambda function is calculate backlog per instance, which runs every minute and calculates the backlog per instance by receiving the current number of messages in the queue and divide it with the number of running instances in the autoscaling group, which later is published as a custom metric to CloudWatch. Let's go over the code for this Lambda function. The main function is calculate backlog per instance. It's configured with two environment variables, QURL and ASG name, which is the autoscaling group name. Firstly, we get the approximate number of messages from the queue by getting the attribute value of the approximate number of messages. Secondly, we get the number of running instances by counting the number of instances in the in-service state in the autoscaling group. Thirdly, we get the backlog per instance by dividing the approximate number of messages with the number of running instances. We need to take care of an edge case where the number of running instances is 0, which might happen when the autoscaling group determines that the last instance in the in-service state is unhealthy and terminating it, and only later it launches a new instance. At last, we publish the calculated backlog per instance as a custom metric to CloudWatch. Metric name is backlog per instance. The dimension is an array of name-value pairs that is part of the identity of the metric. Value is backlog per instance, and the namespace is SQS/autoscaling, which is a container for CloudWatch metrics. The second Lambda function is log autoscaling group events, which is triggered by an event bridge rule. The rule gets autoscaling group events, such as EC2 instance launch successful, and the Lambda function writes them to a CloudWatch log. I use this function for debugging purposes. The second project is the SQS worker. This is a naive implementation of a Dockerized Node.js app. It subscribes to the SQS queue and processes messages. Message process duration is 1 minute. Each time the autoscale group launches a new EC2 instance, a script in the user data of the EC2 instance pulls and runs the SQS worker image. The third project is the Infra. It is a Terraform project responsible for our infrastructure. I'll go over the important parts of this project. This is the AWS autoscaling policy resource. It is attached to the autoscaling group and responsible of scaling activities. We give it a name, then we attach it to the autoscaling group name. Policy type is target tracking scaling. Estimated instance warm-up, we set it to 2 minutes, which is the estimated time until a newly launched instance will contribute CloudWatch metrics. Target tracking configuration is where we define our custom target tracking policy. We define the metric dimension, which is a name value pair that is part of the identity of the metric. The name is project, value is SQS autoscaling demo. Metric name is backlog per instance. Namespace is SQS/autoscaling, which is a container for CloudWatch metrics. Statistic is average. Target value is the acceptable backlog per instance, which is the accepted latency divided by the average message processing time, which you probably already remember. It's important to note that the custom metric values defined here must be identical to the values defined on the calculate backlog per instance Lambda function. Okay, let's start the demo by following the running instructions in the README file of the project. We start by creating the SSH keys. SSH keys must be created on the info project directory with my key name. It will allow us to SSH into our instances. Once finished, you can see that the keys were created successfully. Now we run the Terraform. At first, we run Terraform init, which initializes a working directory and install the AWS provider plugin. Then, we run Terraform apply, which executes the actions proposed in the Terraform plan. Once finished, we copy the Terraform outputs, which is the AWS SQS queue URL and the AWS region, to the publish messages script and paste it there. We will run the script later once everything is set up. Now we run the serverless project. We start with installing serverless globally by running npm i-g serverless. Then we run npm i to install the project dependencies, and finally we run serverless deploy, which deploys our entire service via CloudFormation. As you can see, 2 Lambda functions were deployed successfully. Let's view the AWS console and see the different components created. This is the auto-scaling group created by Terraform. It has a dynamic scaling policy, which is the target tracking scaling policy we created earlier, and currently there is one instance in the in-service state. This is the SQS queue created by Terraform. Currently it holds no messages. Those are the CloudWatch alarms created by the target tracking scaling policy. The first one is a scale-out alarm. In case the backlog per instance will be bigger than 10 for 3 data points within 3 minutes, which means that if the calculate backlog per instance lambda function will publish a value that is bigger than 10 for 3 straight invocations, the alarm will go to alarm state and the scale-out activity will take place on the autoscaling group. The second alarm is a scale-in alarm, which triggers when the backlog per instance is lower than 7 for 15 data points within 15 minutes. Those are the Lambda functions created by the serverless framework code. Before publishing messages to the queue, I would like to show you a useful command that the serverless framework exposes. By running serverless logs -f calculate backlog per instance, which is the name of the Lambda function, -t, you are able to tail the CloudWatch log. This will allow us to view calculation details each time the Lambda is invoked, which is every minute. Once everything is set up, we will publish messages to the queue and see how the scaling works. We do it by running npm run publish on the backlog per instance calculator project. This command runs the publish messages script, which publishes 50 messages to the queue. Let's view the AWS console and see it in action. We published 50 messages to the queue, and we have only one instance running. We should expect a scale-out activity. We can see that the alarm state is in alarm, and if we view the auto-scaling group, we will see that we have 5 instances running. Cool, right? Once all messages are processed and the queue is empty, we should expect a scale-in activity. We can see that the alarm state is in alarm, and if we view the auto-scaling group, we will see that we have only one instance running. Nice! Let's do some cleanup. At first, we run serverless remove, which removes the deployed service. Then we run Terraform destroy, which destroys all remote objects managed by our Terraform configuration. There are important topics regarding this configuration that are not covered in this video. Despite this, I think it is important to note them here. The first one is scaling protection. Messages that have not been processed at the time an instance is terminated are returned to the SQS queue, where they can be processed by another instance that is still running. For applications where long-running tasks are performed, you can optionally use instance scaling protection to have control over which queue workers are terminated when your auto-scaling group scales in. The second one is graceful shutdown, meaning the instance that is about to be terminated stops subscribing to the queue, finished with what it is currently processing, acknowledging the message, and only then terminates. There are two ways to implement graceful shutdown. The first one is using auto-scaling group lifecycle hooks, and the second one is implementing a seek-time handler in your code. The third one is scaling to 0 instances. In some cases, the traffic to the EC2 instances is low, and you want to scale to 0 in case there are no messages. For that, you need to implement a hybrid approach and add a simple scaling policy for the case of 0 instances. This is very effective for cost reduction and optimization. In conclusion, we learned how important and effective it is to auto-scale our application based on Amazon SQS in terms of latency, throughput, and cost reduction. How can we use a target tracking scaling policy with a custom metric to achieve it with a solution of backlog per instance? Please let me know if you have any questions down below. The code is available on GitHub as well as my LinkedIn profile. Please feel free to reach out. I hope you enjoyed and it gave you value. I encourage you to run the code and play with it. If you want to learn more on AWS and all types of coding related stuff, please consider subscribing. Thanks, happy coding!